Hello and welcome again to Environmental Geology. This will be Lecture 6, and the topic today is going to be on volcanoes. And you should focus your reading on Abbott chapters 6 and 7. Now volcanoes I really kind of like. They're a pretty dynamic part of geology. Pretty active stuff on the Earth, and they create some spectacular things that we see on this planet. And so we're going to look at a variety of things with volcanoes today and some of the activities and other strange things that are associated with volcanoes. Now, a volcanologist is obviously a person who studies volcanoes. This happens to be one of the more famous volcanologists here, one of the Kraft family. When I say who are these guys, I kind of a joke about that because in my opinion, being a volcanologist, especially something like this, is a very, very dangerous job. And I think it takes a lot of courage, if not maybe a little bit of craziness, to be a volcanologist and get up this close to this kind of activity. In this case, you can see this individual wearing a protective suit. Even some of these volcanologists have gone far enough into maybe attempting to want to design a special metal kayak or canoe to float down some of the lava flows and see if they would have the first experience. Kind of extreme sports at its best, I guess. But it's a pretty wild group. And so job security as far as a volcanologist, there's a table in your textbook. The first time I've seen this one talking about how many volcanologists got killed in a number of volcanic eruptions here. And you can see that's pretty high numbers for a group of geologists. So there's certain professions that we know of that are pretty bad. I don't know about job security, but those who work with the more violent types of eruptions, the explosive ones we'll look at in more detail here later on, are the ones who are in trouble and have been killed over the years. How do they get killed? Well, one way, during an eruption explosion, to have something land on your head. Kind of a neat little cartoon out of your text. In this case, you got a large rock ready to just fall out of the sky and smash it. We call these bombs, or volcanic bombs. And in this kind of collage of pictures, you can see a number that are rather large. They'll get even bigger than this, Volkswagen size, Volkswagen bug type size bombs coming out, and all the way down to fine ash. So we'll be looking at some of these explosive materials that are coming out. The one on the bottom right, of course, is still hot. You can still see the glowing material inside that. So there is danger in some of this. Now, volcanoes also have inspired other things. A lot of artsy, craftsy things that we see from materials made from volcanic stuff, or legends of why the volcanoes are there. I know on the island of Hawaii, the Hawaiians have their legends about Madame Pele, who is the goddess of fire, who, because of her, she's created the land that they live on and provided them what they have. And in fact, there's even a poem or two, I'm sure, written about her. There's one of the poems on the left. It's in Hawaiian, and the interpretation is English on the right. So it's not just, science all the time. It can inspire other things. And she's constantly on the move. And we're going to see what that means later on in terms of like the Hawaiian Island chain itself. Before we do that, though, I want to introduce you to a basic background of rocks involved with volcanoes, and of course they're igneous rocks. So I want to go through some terminology and some definitions of things dealing with igneous rocks, and then we can go from there to go back into very specific types with volcanoes. Now, igneous rocks form from the cooling and the solidification of magma, or the hardening of that magma. And of course, magma we define as liquid rock. In certain zones within the Earth, rock is completely melted into a liquid form. And it will move and migrate, and when it gets into a colder environment, it's going to crystallize and harden. So depending upon what the composition of the magma is, we're going to get a different variety of igneous rocks. Now, sometimes this magma will remain below the surface of the Earth. It never gets to the outside, never becomes a volcano. And we'll see why that is, again, in just a little bit. But we refer to these magmas that stay below the surface as plutonic magmas. They stay inside. So we use that idea and say they're intrusive. They remain inside the Earth. Plutonic magmas. Now the ones related to this particular chapter on volcanoes are those magmas that do make it to the surface of the earth. We categorize those as volcanic lavas. Once magma comes onto the surface of the earth, we change the name from magma to lava. And so it's come on the outside of the earth. It's considered extrusive in nature, being on the outside and cooling off on the surface of the earth. So magmas are liquid rocks. When they cool off, they form a whole variety of igneous rocks. If they're intrusive, we call those plutonic. If they're extrusive, they're volcanic, the focus of this chapter. Now, how can you melt rock? I mean, rock is made up of individual minerals, crystalline natures and different types. And so how can you actually get something to happen to melt rock? Well, I think it's the first parameter would be obvious. You increase the temperature. By jacking the temperature up to a particular point, certain mineral will have melting points and the atoms will dissociate, the bonds will break, and it becomes a liquid. I think that's the one that people think of most often. But where magmas form deep in the earth, pressures are very, very high. And so you may have temperatures elevated above melting points inside the earth, but they don't melt because the pressures that squeeze them together are too high. The bonds can't break. So one way is say, okay, let's get this material that's really heated up closer to the surface of the earth and decrease the pressure, thus allowing the bonds to break. So increasing temperature or decreasing pressure. And another way is to have water, add water to it. The presence of water vapor in magmas lowers melting points of certain minerals. And so in doing so, pushes that process quicker to turning things into liquid material or magma. So to melt the rock, 3 specific conditions. Now, where might this happen inside the earth? Okay, we're going to look at some of the zones where this would take place and what might the heat sources be in particular in this case. Now, in terms of the heat, as you go deeper and deeper and deeper in the earth, the temperature goes up and up and up. I always love that movie, The Core, when they kind of go down inside the earth and check out the different zones and stuff. You got to look at some of the science and look at some of the physics with that. There are some things are off, but it's a neat adventure, at least in terms of a movie. But geothermal gradient simply means as you go deeper in the earth, the temperature of the earth, geo, increases. Just the natural geothermal gradient. It's hot down there. And in some places, the heat is concentrated. Some of this heat that gets concentrated inside the earth and the mantle may be coming from the deeper core of the earth. And through conduction, that heat will move into the mantle and heat up the zone. And once you heat things up, you can slowly make it rise towards the surface where the pressures are lower. So hot mantle plumes can dissipate heat to different zones as they move upward through the interior of the earth. Another source of heat is where we have materials, elements inside the earth that are radioactive. Uranium and thorium or rubidium. Certain elements are radioactive, and one of the byproducts of radioactive decay, is heat. Now, the radioactive elements inside the earth are not uniformly distributed. There are some zones that have more radioactive material than the others, so you'll have some zones that are hotter than others. So that's all we're trying to do, is find ways to heat things up inside the earth. Now, in this cross-section image from your textbook, I want to point out several kind of parts of where this heat concentrates. Okay? And so we've already talked about plate tectonics a little bit and related volcanoes a little bit to plate tectonics. But let's use this diagram to talk again about some of the processes associated with this. Over on the right-hand side of the diagram, you have an uplifted mid-ocean ridge. All right? Now, the reason why this ridge is physically uplifted or higher has to do with the fact that below it is some kind of a hot spot, a zone where the rocks have heated up and they're rising upward, just like in a hot oil lamp. All right? Now, the source of the heat could be the Earth's natural heat down here, could be mantle or core heat, or radioactive decay. Whatever the case is, we have some kind of a hot spot. Now the rocks here are not liquid. They're simply superheated above their melting point by this localized heat. And as that mass slowly rises up because the increased heat has made them less dense than the surrounding rocks, all right, eventually they get closer and closer and closer to the surface, and what happens to the pressure? It drops. So at some point there's a certain set of minerals in this mantle material that they're now below their melting points. Right? And so just part of those minerals in that material will melt. So this has led to several kind of phrases we refer to what happens to this stuff as it melts. All right? I want to talk about partial melting. That phrase simply means that part of the mass in that uplifted hot spot melts. Not all of it, just part of it. A certain group of minerals that have lower melting points. And the fact that we've gone upward and the pressures have gone down, we've kind of gone through decompression of pressure. So the other phrase that's out there is called decompression melting. They're both processes that we're kind of talking about. Whatever the case may be, is what happens is when you partially melt through decompression melting these hot spots below these mid-ocean ridges, what you produce is a liquid rock. They're trying to show you in black that pushes upward and squeezes out and then cools off on the seafloor. It becomes solid rock. Now this rock type will have a specific igneous rock name. It's going to be called basalt. And we'll come back to that term basalt again. All right? Another place associated with the generation and creation of magma has to do where the plates are hitting kind of head on. In this drawing we're showing this dense, heavy basaltic crust, oceanic crust, approaching and moving at and towards a less dense, lighter weight continental crust, which is more granitic. So the heavier, denser material will begin to dive back down into the mantle. And it goes back, as it goes back down with it, it's dragging these sediments on top of the crust with it, which have what in it? Water, seawater. Aha, water. Get that now? You got this idea of having another one of those variables to help melt things. So as we pull that material back in here, zones in here where this water is released will help, again, melt the material in there, lower the melting points, and we can create different kinds of magmas again. If we melt oceanic basalt crust, we'll create another kind of igneous material. Or if we're in this wedge in here between the crust, this is still the upper mantle. If part of that melts, again, for the same reason, by the release of this water, we can again generate basalt magmas, we can generate different lighter weight magmas, and since they're liquid, they move upward. They move towards the surface of the earth. Well, how fast can they move? What controls how this liquid stuff moves, how quickly it moves, and whether it's going to stay inside the earth or whether it comes out in the form of a volcano? In this picture, in the cartoon, we're showing some of the magmas. Let me get the mouse back here. Over here on this left-hand side, these little blobs represent magma chambers. Now, if they stay down here and solidify underground, miles down, they're plutonic. They're intrusive. But if they make it to the surface, then they become extrusive or volcanic. And so depending upon a variety of conditions, they can be very mellow eruptions or extremely explosive. And we'll look at some of those characteristics in a bit. All right, now what tends to make up the materials that's coming out of the earth? This table in your text talks about the common elements in the earth's crust. And I only want you to remember two main things here, because we've kind of talked about this a little bit earlier on in the course maybe, but oxygen and silicon are the two dominant elements in the earth's crust. Oxygen and silicon. So we've got these silicate minerals like olivine and pyroxene and amphiboles and quartz and the feldspars. When you look at crustal rocks, that's what makes up most of those rock types. So that silicate category we looked at earlier will be light-colored minerals, dark-colored minerals. You don't need to remember the percentages on here. Just remember that the two most dominant elements in the crust of the earth are oxygen and silicon. Of course, aluminum and iron, you know, they're pretty good in amounts, and maybe some calcium, but those are the two biggies. And they're going to be involved in this classification then of how we categorize igneous rocks. So this next table has to do with the classification of igneous rocks And the way we base this classification is to look at two conditions, two features. The composition, which means the mineral makeup. And the second characteristic has to do with what we call texture. And texture has to do with what kind of crystal size, if any, the crystals have as this liquid rock cools off. So you're going to have two kind of categories, composition and texture. And I want to create two kind of columns or tables here for us to throw some names at you. On the left will be the extrusive types, the volcanics. And on the right will be the intrusive types. And these are the two common rock names, igneous rocks, of extrusive and intrusive rocks that have a certain characteristic, a certain composition and texture to them. Basalt on the left and gabbro on the right. And I'll come back to these in just a bit. I'm going to finish the rest of the diagram and show you some other names of rocks, andesite and diorite, and rhyolite and granite. We'll kind of look at this more closely now. All along the left-hand column are the extrusive types of common igneous rocks, basalt, andesite, and rhyolite. On the right-hand side, gabbro, diorite, and granite. Now those rock types differ because of two things, composition and texture. And kind of look at that. All the rocks that are on this left-hand side are going to be extrusive. And they're going to have a certain grain size. The crystal sizes that you can see are very, very, very tiny, tiny crystals. In fact, sometimes you can't even see these crystals with the naked eye. They're far too small, and there's a reason for that, because of this extrusive characteristic. All right, they're going to be what we call fine-grained. On the right-hand side, the crystals are a lot bigger. You can see individual crystals with the naked eye. So there's textural differences. Grain size is a texture. On the right-hand side, big crystals. On the left-hand side, little crystals. That's one difference. The other difference has to do with what minerals make them up, what types of silicates. Let's take a look at basalt and gabbro. Basalt and gabbro are essentially the same thing as far as composition is concerned. They're made up of dark-colored silicate minerals. The key thing there is they're dark-colored, so the rocks are dark-colored. Certain types of pyroxene silicates, a little bit of olivine. Certain types of darker colored feldspars are in these rocks. So compositionally, basalt and gabbro are the same thing. The difference is in the grain size. One's big on the right, the gabbro. Basalt is fine-grained. Now, as we move down the chart, you get the lighter and lighter colored rocks and minerals. Rhyolite and granite, again, are the same composition essentially. A lot of quartz, a lot of light-colored minerals, light-colored feldspars, some of the micas. So the rocks will be light-colored on the average. The only difference is what? Granite is coarser grain, bigger crystals. Rhyolite's tinier. So the middle group, andesite and diorite, they're kind of intermediate in composition, intermediate in color, kind of halfway between the dark and the light types of igneous rocks. So you can use this chart to talk about two things, compositional differences and texture. And the texture is going to be based on what happens to whether they're intrusive or extrusive, and that has to do with something else, kind of the cooling rate. All right, igneous rock types. Let's kind of look at this chart maybe another way, very similar diagram, but in this case they talk about the percent of silica, the magma type, SiO2 less than 55%. That's considered low silica content. If you move down the column to the bottom where it's greater than 65% silica, okay, SiO2, those are those two common elements in the crust, then you're going to have a high concentration of silica. That's going to make what happens to the magmas to behave differently. It has to do with the stiffness. Now, if you've ever bought oil to put in your car, you talk about oil when you purchase, talk about viscosity or the weight of the oil. A kind of a generic way of talking about that viscosity is how stiff it is, how thick it is, whether you're getting about a thick milkshake or real runny milkshake, okay? So I'm going to throw the terms runny and stiff at you and this silica percent now, and then we'll talk about its real name called viscosity. But it has to do with this silica type of percent that's in it. Let's take a look at granite. Granite is an intrusive plutonic rock. the magmas, granitic magmas, when they're in the liquid form, have a high concentration of silica. See these little silica tetrahedral building blocks down here in the bottom right? There's a lot of that there, so this thing begins to grow and mesh and get stiff real quick, thicken up. Kind of like adding flour to make gravy. It stiffens up. So all of a sudden you got this liquid material that starts to stiffen up more quickly, and as it rises, it does what? Cools down. All of a sudden it gets too hard. It can't move. It stays inside the earth. So granitic magmas, because of this stiffness, all right, remain as intrusive plutonic rocks. Basalt, at the other end of the spectrum, has a low percentage of silica, and magmas low in silica with independent tetrahedrons do not readily, join up and make this mesh in the liquid with these silica tetrahedron building blocks. And so what happens is it remains kind of runny, more liquidy. Well, something that's more liquidy can move easier, can move faster. And what can it do? Make it to the surface of the earth, become extrusive. So basalt, again, extrusive is runny. So remember, in case I pull this on the test or something, that basalt magmas are more runny or low kind of silica types, whereas granite or granitic magmas are stiffer, have a higher percentage of that silica in it. They're stiffer magmas. So this concept I've been talking about, the name we use is referred to as viscosity. Okay? Factors controlling viscosity. Viscosity is a measure of that stiffness, how fluid the magma is. Well, obviously, if you have, like I said, a lot of high concentration of silica, all right, compositionally, you got high silica content, you have a higher viscosity. That means it's stiffer. Low silica, runnier. Low viscosity. The presence or absence of gas also is a factor that comes into this, and so I'll just say that the lower percent of gases in the magmas, then the higher the viscosity, the stiffer it is. As far as temperature is concerned, obviously if you have lower temperature, turn the thermostat down, cool it off, it's going to start to stiffen up. If it's stiffer, that means it has a higher viscosity. So temperature, presence of the silicon dioxide, or the presence of gas. The amount of gas in that determines how stiff or runny these magmas are, whether they're going to become extrusive or intrusive. So let's go back to our plate tectonic map and look at some places where magmas are generated. They're more of a map view. Let's take over here in the Mid-Atlantic Ridge, kind of the picture I was showing you in the cross-section. There's probably a hot spot under here somewhere along this ridge. There's an upwelling, partial melting, and you have an eruption of magma that comes out there. Well, in these mid-Atlantic, these mid-ocean ridges, like the Mid-Atlantic Ridge, out here in the Eastern Pacific, over in the Indian Ocean on the left, magmas that erupt from mid-ocean ridges is kind of mellow. Most of these are, of course, deep down, thousands of feet below the surface. The pressures are higher, the temperatures are very cold. But when that basaltic magma oozes out, we would say it's kind of mellow volcanic activity. It's not explosive. Under the island sequence of Hawaii, there's a fixed hot spot as the Pacific plate moves over that. And so the kind of activity in Hawaii would be considered mellow because of the kind of magma, the more runny, soupy basaltic magmas. So anywhere where you tend to find basaltic magmas, volcanic activity, you could just say it's kind of quiet or mellow. It's not super dangerous, all right? Go up to Iceland. Iceland is simply where the Mid-Atlantic Ridge up here is elevated above sea level. A much hotter hot spot, bigger ones underneath there. And so you can, if you go up to Iceland, you'll see basaltic magmas, and it'll be kind of quiet. The island's not blowing up. It's not explosive. But if we look at head-on collision boundaries like North America with the Juan de Fuca plate, or down in South America with the Nazca plate, those are convergent boundaries. And when you got these two great big trucks heading head-on, and that subduction, the kind of magma is going to be different. It's going to be a little stiffer, kind of halfway between the two types of basalt and granite, and it gets stiff, there's a little more water. That all sets up to be very, very eruptive and explosive. So let's take a look a little bit closely at Hawaii. If you look at the Hawaiian Islands right now, the Hawaiian Islands are a series of islands in a chain, very broad, kind of spread out, large area, thousands of feet thick that come up from the seafloor of the Pacific Ocean. The actual island you see is just a little tip at the top of that piece. It's really spread out like a broad shield. So they classify volcanoes like the Hawaiian Islands as shield types. I want to write that down. The shield type is the style. It's broad, kind of flat and spread out because the lavas are runny. They're soupier. They'll spread out more easily over a broad area. And the kind of igneous rock that makes up Hawaii predominantly is basalt. Now right now, the activity where things are going on with this very mellow, slow eruption is on the southeast side of the big island of Hawaii, over here, and just offshore under the sea. An underwater eruption going on, a brand new little island that eventually will emerge above sea level called Luihi. So this is where the activity is right now. We're going to look at some of the pictures and some of the things we're concerned about. Even though it's mellow activity, we're still concerned about what might happen in Hawaii. Now here, if you go back to the Oahu, let me go back real quick to this picture on the map. Oahu is further northwest. The activities on the Big Island, all these islands of Maui and Molokai and Oahu and Kauai, there's no volcanic activity on them now. They're not over the hot spot. They're old, they're being eroded, it's kind of quiet. There's volcanic rock there. If you go to Oahu, like you can see in these series of pictures, and look at the old craters and stuff, the whole island is made up of nothing but lava flows and, and welded craters that are mixed together. Not a lot of activity going there, but if you go to the Big Island of Hawaii, and you go to the main active vent right now near the Kilauea volcano, the main vent's called Pu'u'o'o, and it's spelled just like it sounds. Might want to write that down, Pu'u'o'o. Pu'u'o'o is the main vent. And here you can see a nice, quiet, frothy, ash being spread up, a lava flow coming down, nice and active. A lot of these flows will go through the forest, through people's homes, all the way to the beach, creating new real estate. You can go and watch it. You just want to be very, very careful about hiking around on it. Because sometimes it might look like the crust is hardened, and right below it, just a quarter inch or half inch, it's rock temperature still flowing and liquid at 1,500, 2,000 degrees Celsius. And occasionally somebody will have a foot, their shoe will go through that, and you've got to be, very careful in these areas. So geologists who live on the island of Hawaii working for the U.S. Geological Survey are constantly keeping an eye on the tourists like you, but they're constantly monitoring what's going on in Hawaii, where the flow's going, which are the new ones, which are the fresh ones, to warn people. And they're checking out what gases are emanating, because when we can calculate the gases, it helps us understand a little bit how fast the magma is moving or where it's coming from. So in the case of this kind of collage of pictures in the top left, they're using a laser beam to measure from point A to point B to create a map. On the top right-hand side, you're looking at a little mini seismograph analyzing micro-earthquakes to see where the magma might be shifting and moving to underground. Over here, they're collecting samples in the lower left-hand corner to do chemical analyses of, and sometimes doing gas analyses. They'll put a probe into the soil and calculate, well, what percentage of these different gases are coming out? What does that mean? To use that to analyze it. Over here, they've got a GPS station set up, kind of fancy, again, to monitor what's happening to the changes in the island. Even though it's mellow activity, we still want to watch out for it. Now, one of the other newer technologies we're using, I want you to write this down. The acronym here is SRI. SRI. What SRI stands for is Satellite Radar Interferometry. As a satellite passes over the Earth, it sends a radar beam down and bounces it off the surface of the Earth, and it comes back up to the satellite. And it records that in very exact vertical elevation differences. Then the satellite goes around again, takes another radar picture of the same spot. If the ground shifted ever so little, and you take those two different passes of data and you crisscross them, take the databases and have the sine waves or the waveforms, the frequencies interfere with each other, if there's no change, nothing happens. But if there has been a change through that interference, it creates patterns on our maps that we can produce that look like little mood rings And so these colored rings here tell us exactly how much the ground shifted up and down vertically. A really cool new technology to measure movement of the Earth. In this case, they're using it for volcanic movement, magma moving towards the surface maybe. So anything we can do technologically to unravel that, we want to know. So we keep monitoring all this stuff, keep checking it out. And here you can see, it's pretty thick on the roof wall where they're standing, but there's a lava tube through there, folks. And you got to be careful if you're out there, because you can get around on the island and be on your own. You're just going to make sure you're not going to some new fresh place. So they're measuring temperatures and looking at the composition of the magmas. But one thing I want to remind you about the gases that come out of these, again, is that there's carbon dioxide, there's carbon monoxide, there's sulfur dioxides, different kinds of gases that can be pretty toxic and lethal to living things. But there's one thing that doesn't come out of volcanoes as a gas. No free oxygen. Oxygen in our atmosphere came from photosynthesis mainly. Maybe a little bit of photochemical dissociation of the atmosphere by ultraviolet light, but no free oxygen comes out of the volcanic vents or during those eruptions. Now, if you wanted to go down to one of those tubes and check it out, here's kind of what it looks like in an old lava tube inside. You got the roof of the tube, but at one point in time, if we go back to this, there's the top. If you were down in here when that's going on, you got a river of hot lava flowing right through there. Even has a little bit of an old levee. And you can see the streaky lines on the side where that stuff had moved and slid by. And these tubes become kind of hollowed out now. So all underneath the island of Hawaii are all these kind of little chambers and tubes that are down there. Lava could still go into them. You go on the old islands, though, they're all, you're pretty much empty and a good place to explore and check around. So lava tubes, the underground plumbing. In this picture where the lava oozed out is a special style of lava. It's got this kind of ropey, kind of texture, shiny surface to it. I'll give you the name of that in just a bit. But to me, this is just beautiful. This is artsy to take a look at that stuff in the colors. You can see the heat as it just advances and slowly rolls, and the crust will cool off and it wrinkles on the top, creates a kind of ropey kind of texture. Well, the name to that ropey textured type of lava, basaltic lava, here's a Hawaiian word for you to learn, pahoehoe. Okay, on the bottom right, pahoehoe is a type of basaltic lava that has a ropey texture to it. And on the top half of the picture, this pahoehoe flow came in contact with another style of lava that we refer to as a'a. And a'a lava is really rough, really blocky in its nature. And this has to do with a little bit of the temperature characteristics of the flow at the time and the percentages of gases that can change that. But you get this smooth style, and you can get this ropey style, or this blocky, rough style. One thing that may not show up real well on your screen, but in the middle, between the two, like where the cursor is kind of moving back and forth, looks like dried grass, little golden shiny things in here. That's another form of lava that actually is glassy. And I've got some scanning electron microscope images of what that actually looks like. It's a different character. Now you can go out to some of those and scoop this up with your hand. You look, it goes, does this look like hair or dog hair? No, these are actually real fine strands of glass. Under certain conditions, when that magma comes out and it cools just instantly and freezes, no minerals can form. We say that's a glassy type of texture, and so this fine grained stuff is referred to by the Hawaiians as Pele's hair. All right, here's that kind of golden stuff in here in the middle. It looks like strands of hair. And under a powerful scanning electron microscope, an SEM, you can see this really smooth, glassy surface, even some of the gas bubbles that got stretched out, an even tinier strand. See how it got twisted as it came out through the air? Excuse me. Pele's hair. Kind of a bizarre type of thing. Very delicate, obviously. If you get the chance to go scuba diving over here, check out what's going on along the coastline when the lava flows come to the coastline area. All right. Here you can see the lava flow on Hawaii come into the sea, the contact and all the steam venting off and new real estate being created. Right at that boundary, a lot of these types of rocks, especially if they're real frothy and full of gas, some of these chunks float. Picture in the top left shows a large sample that's actually floating in the water because there's so much gas trapped in it and gas pockets that are not connected so it doesn't sink. And here's a diver in the bottom right. He's got his little rock hammer in his hand. He's going out there and banging on these things. So volcanologists, whether they're out there next to an explosive volcano or off the coast of Hawaii, are still kind of pushing the limits to see what can happen with these kinds of eruptions. So under a scanning electron microscope, here's what that real fine, frothy, glassy kind of lightweight stuff looks like. The rock name is called pumice, P-U-M-I-C-E. Dentists used to use this pumice powder in paste to help, polish and clean the teeth. But you can see there's a lot of voids in this thing, a lot of open holes where the gas bubbles used to be. Kind of very delicate, soft material, very lightweight. And there's even more bizarre things. Here's another oddball one I told you I'd throw at you. This thing called limu opele, another Hawaiian phrase for some very strange kind of flaky looking pieces that come up where these lava flows and erupt into the sea. So under a scanning electron microscope, there's all kinds of new things we could look at to figure out what's going on with flows. But back to the disaster part, on the main island of Hawaii, in the village of Kalapana, the lava flows continually went through the towns and burned the houses, and people had time to evacuate because we're in a very mellow kind of volcanic environment. Sometimes it will burn the trees, sometimes it moves around the houses, the fences, just depends. But it doesn't, you can't stop it too easily. Here's another spot on the earth where we've got some mellow activity but affected a lot of people quite dramatically in East Africa. In the East African Rift, way over here by Lake Victoria. Get close to, one of the small lakes that's not labeled on here, Lake Kivu. The little town of Goma is downhill from a volcano up here. And this volcano erupted, and lava flows came down into the city, and I'll show you some of the pictures. Now, people had time to move. People had time to get away. But the flow was so large, it was very devastating to what happened in this rift. Here it's going across the airport, completely covered it up. Here's going down through one of the main streets in downtown on the top right and the bottom left, here across the main field by the airport. And a lot of people in this town were displaced. And they could move. Now here they're waiting to the last minute to grab their belongings and get out. But they had some pretty treacherous stuff to get around to get out of here. Not a lot of people died at all with this. Because it's slow moving, you can forewarn people, you can get them out. But they're homeless, they're displaced. And this was a pretty large community that got moved out in Goma. I thought I'd show you some of these pictures of the underwater eruption of lava, whether it's in the mid-ocean ridges or just off the coast of Hawaii. It could be thousands of feet down in deep eruptions. It's still mellow. And when it comes out and oozes and squeezes out of the seafloor like that, it creates these kind of bulbous piles of lava. And so the special name we as geologists give to this kind of deep submarine eruption material is pillow lava. So you're going to need to remember the term pillow lava. All right? Deep eruption of stuff. It's got a bunch of piled up pillows or bulbous stacks of these things. Let's see if this will kick in. Here's some action of how that underwater eruption creates that rounded bulbous shape. Let's see if I can make it happen one more time. So pillow lava is evidence in the rock record of what? Submarine eruptions, undersea, underwater eruptions, usually deeper water. Of course, we come closer to the surface of the ocean or the lakes where the pressures are a lot less. When you get that hot magma coming in contact with seawater, that water creates an explosive situation. So as lava, ranges begin to get higher and higher and higher from the seafloor and get closer to the sea surface, all of a sudden, like we see out here in the Solomon Islands, that's not a bomb, that's simply eruptions of magma coming in contact with seawater. And everything just blows to bits and everything's fragmented. We call this special kind of situation a phreatic explosion, phreatic implying the water involvement. Now if it can explode enough, all of a sudden you can start to see on the right-hand side a cinder cone building up, maybe a little water still coming in there. Eventually this will build above sea level, and sea level or seawater doesn't get in there anymore. And then you get those nice mellow lava flows coming out, harder rock, and you establish an island. If this were to quit though, maybe just the waves could eventually erode and bash that down. So phreatic explosion, kind of a separate one. But what about the big ones? What about these really dangerous, dynamic, large types of volcanoes? I've circled some places on the map that will look at a few of them and examples of these. But most of these occur at convergent plate boundaries. The main head-on collision with subduction zones that create andesitic type magmas that are very stiff, high water content, and they're still extrusive in their nature, but they'll pile up very, very steep. So we're going to look at some places like here on the western part of North America and a few others to focus on these large earthquakes. One of the types of eruptions that occur at these convergent boundaries is where, coming from the top crater on these volcanoes, this hot, dense mix of gases, ash, and rock that comes just blowing down the side, the slopes of these volcanoes extremely fast, up to 150 kilometers per hour. Here's an example of one at Mount Unzen in Japan. You can see there, this gentleman here is running. They apparently did pick him up. They were booking it with their van there to get out of the way. But this cloud of ash, if you get caught in that, you are incinerated. You're just caught in, incinerated very quickly because it's so hot. We refer to this kind of dense cloud of hot ash and material coming down the side as a pyroclastic flow. A pyroclastic flow. The pyroclastic flow is hot, dense, mixed gases, ash, and rocks. And most of them will move faster than you're going to be able to get out of the way. This was, by the way, in this photograph when they caught it, was nearing the end of the flow. Kind of made it down to the bottom of the hill in this area and then quit. It kind of had died out by that time. Now let's see if this kicks in. Watch this. This is down in Montserrat in the Caribbean. And what you're watching is a pyroclastic flow that is blowing down the side of the hill, going out into the ocean. If anybody were out there kayaking in that area, they probably would have been killed very quickly in that case. Now I want you to kind of watch the bottom right-hand corner. I'll play it several times. Watch what happens to the sea right here. See that disturbance? All kind of a mixing up of frothy white wave action. That could be maybe gases blowing out from there, or maybe a school of fish that just all of a sudden, like, whoa, temperature shot way up here. We got this hot superheated stuff blowing out into the ocean. Any sediments in it eventually then of course just wind up in the sea as deposits and the waves working back and forth. But this was a dangerous moment on Montserrat. A number of people got killed in attempting to evacuate that island. Here's some of the aftermath on the island. A lot of the houses were destroyed. Here's one of these like 6 to 7 foot tall kind of English looking telephone booths. This material this young lady's walking on is all of this kind of fused material of the pyroclastic flow. Pretty dramatic stuff. Here's Mount Pinatubo in the Philippines in 1991. An Air Force base was on that island at the time. And these huge, tall, high volcanoes. Now I told you Hawaii was a spread out kind of volcano called a shield volcano. The steepest volcanoes in the world, because they're so high, kind of up into the stratosphere, we classify as stratovolcanoes. And when they blow their top, they're extremely dangerous. A lot of ash and bombs and gases are released, pyroclastic flows you don't want to be around. These have been some of the most damaging types of volcanoes to humans. Mount Pinatubo in the Philippines in 1991. There's another name for stratovolcanoes your book may call composite volcanoes, but nevertheless they're, here you can see it's in a fury what's going on right now. A lot of the steam clouds and debris in this thing on the left-hand side. Pretty nasty. You'll even see lightning bolts come blowing out of these clouds because of the charges that build up. Whatever it is, you don't want to fly through there. Whether it's a jet or anything, the ash the glassy material that's in that atmosphere will destroy the turbine engine. You're going to lose an engine flying through it. So just to remember, one of the dangers, if you're with a pilot or somebody says, let's fly over this thing, don't even try. You got to go around it as far as you can. This happens to be an example of one of those in Vesuvius, Italy. Okay? So they can pose not only danger to what's going on the surface of the Earth in a nearby area, but also way up in the atmosphere, 40, 50, 60,000 feet up. You don't want to go flying through them. This happens to be what happened in Vesuvius when some of these flows came blowing down and covered the villages, buried them in their homes. You can go over to Italy and see this, and it's quite a spectacular type of museum, museum to walk through and see all the materials that were preserved, and of course a few body casts like this one also ended up in there. And Vesuvius in Italy is one of several volcanoes. Vesuvius is still active today, still erupting, so the Italians are constantly monitoring to see what's going on. With the increased population, the chance for more people to get killed, more cost to loss of homes and so on. Here's another one in Italy, Etna, just recently. I took off the web from one of these satellite images, Iconos. Spectacular eruptions of these types of volcanoes. You can see the dark lava flows going down the side, the extreme high steam cloud, vents coming off on the sides of the volcanoes. Here's some of the volcanologists on Etna. The bottom left picture, I think, is really wild. You've got this steam constantly coming out, but once in a while it kind of puffs and blows, like if you're puffing a smoke ring with a cigar. And that steam will actually, Earth is making some really cool, smoke rings. This is one of the rare types of situations seen in Etna. On the bottom right, you can see some of the damage to the village through that area. It just completely wipes out the homes. So what are some of the things that are falling out of these volcanoes, these big stratovolcanoes that we'd want to be concerned about? On the top here, all right, we lump under what we call tephra types. Tephra types. Tephra is the stuff, the plastic material that's blasted or blown out usually in some fashion. So if it blows up in the air and it falls down through the air, if it's really fine powdery stuff, it's called ash. It's a little bit bigger and coarser, we call it cinder. And if they're huge, they're bombs, like we looked at earlier. But if it comes rolling out of that crater instead of being blasted up in the air and flows down the side, it's our pyroclastic flow. Those are the tephra types. And so these cinders and ashes and bombs and these flows are interlayered on the sides and the slopes of these steep, really high volcanoes, these stratovolcanoes. And they're high enough to get glaciated and have snowpack, collect a lot of rain, and all of a sudden they can soak up a lot of water. And once in a while, all that water that's absorbed by these unconsolidated layers, the ash and the cinder, will come blowing down the side of the volcano as a mud flow. Well, the special name we give to a volcanic mud flow is a lahar, on the bottom right. L-A-H-A-R. Lahar is a volcanic mud flow, not to be confused with just a regular type of mud flow. All right. Not sure if this was jumping too fast. I want to now move over a little closer to home here. One of the more recent eruptions we had in the United States was Mount St. Helens. And of course, we talked about plate tectonic conditions earlier. Mount St. Helens is one of many steep stratovolcanoes from Northern California all the way up into British Columbia that are still active today. Mount St. Helens blew its top, and we'll look at some of those pictures. The reason why that's happening is what? We've got the Juan de Fuca plate subducting beneath those states. We've got partial melting. We've got the production of andesitic, stiff, thick, water-rich magma, and it creates real high mountain ranges called the Cascade Mountain Range. And one of those active things is Mount St. Helens. They're very dangerous and they're very explosive. And these are the ones we're really monitoring a lot. So if you ever move to this part of the world, or any of these regions with these stratovolcanoes, be aware. Get online and find out what things that particular community has for safety, for evacuation, what you need to deal with. Again, so it's that subduction zone. And get the production of very silica-rich, water-rich, rhyolitic to andesitic magmas. We're talking about a kind of formula for explosive, viscous types of volcanic activity going on. And that's what Mount St. Helens did. That's what occurred at Mount St. Helens. This table from your textbook shows some of the more active volcanoes in that range at a recent geologic time. Mount St. Helens has more kind of little symbols on it. Been very, very active. 1980 was the most recent one. Mount Shasta in Northern California had some activity in the early 1900s, not too long ago. So for you to remember, I think I'll have a question, or there's one on Blackboard about Mount St. Helens and Mount Shasta are the two most active volcanoes in the Cascade Range. Of course, out in Washington, Mount Rainier is the biggest one, over 14,400 feet high, and if that one were to go, we'd have some pretty interesting things going on in Seattle, in that general region. Here's what happened to Mount St. Helens. It wasn't just a vertical explosion. In the sequence of pictures in your textbook, they talk about how the magma began to bulge up and push towards the side and oversteepen the side. It made that steep side unstable. And all that happened all of a sudden was a large landslide, and all that weight of that rock on that oversteepened slope on the bulge slid down, uncorked it, got rid of the pressure, and kaboom. You had this tremendous lateral explosion blowing right out the side, this blast, about 600 miles an hour, I think. And did some interesting things to everything in its path. Killed around 90 people. It was kind of a devastating thing in our recent past here. This is Mount St. Helens before. Nice, beautiful lake, a very beautiful, symmetrical, high, snow-capped volcano. And here it is afterwards. Blew that whole side out, blasted right at you, tore all the trees off the mountain ranges out here, and most of them just slid back into the lake. All this gray stuff here are logs. These are logs, huge logs in the lake with ash. This became a very unstable spot, potential for lahar deposits. They were pumping water out of the lake to keep that from building up and filling up, because downstream from that, there's all these little communities. Now, its vegetation has grown back quite rapidly, but it's not back to the way it was, and it still could blow another time. So we are constantly monitoring it. I thought I'd show you this one of even off the Aleutian Island chain. The Aleutians are all volcanic because of collisions of the Pacific Plate and North American and Eurasian Plate. But offshore, right over here in 2003, just last fall, they were out there with some radar, and sure enough, they picked up on a brand new kind of submarine volcano cropping up with the lava flows moving down. So a new technology to see underwater now. We're checking everywhere we can to keep an eye on these things. So radar is another type of tool. Here's your SRI. This is down in South America. Unfortunately, this image is backwards. I'm not sure if you really look real close, but it's these mood ring patterns where something's causing the volcano to move upward. The magma is rising towards the surface. So monitoring. Well, there's a few other goofy big volcanoes in our past that we have studied and looked at and have a concern about. Because Mount St. Helens, Mount Pinatubo, Mount Etna, they're big, they're dangerous, but they're nothing like these when these erupted, these super volcanoes. They were huge in their eruptions. And they're part of a process where a big area of magma erupts out, and underground the magma chamber becomes devoid, and the surface of the earth just collapses back into a big centralized collapsed caldera. Now, one of those areas that's being looked at today is in California, called Mono Lake. This is the lake in the depression. The lake level's going down because of climate changes and taking water out of the lake and diverting it to some other communities. But this whole region was one big volcanic eruption in the past, Mono Lake. Another spot out in California, the Long Valley Caldera in California. The Long Valley Caldera. Now, it doesn't look like much. It doesn't look like a volcano, but in the past it was. It was huge and extremely explosive. Here's some of the other map studies they're looking at. They're studying the springs, mapping the cross sections, looking at where the magma chambers are below the surface now with seismic data, calculating the gases that are venting out, looking at the rate of seismic activity. This stuff is picking up slowly but surely, and they're saying, are these indicators for another great big huge eruption? Mount St. Helens didn't bother us in Kansas. If this one goes in Long Valley or Mono Lake or another one, we will be affected. Here they're looking at the seismic activity and the shifting of the ground. So there's a lot of geologists in these regions studying these ancient places, the big, old supervolcanoes. And yes, they're picking up on increased seismic activity. You can get on a website daily. They constantly have the updates of where the earthquakes are. Crater Lake, kind of the southern end of the Cascade Mountain Range, is a smaller collapsed caldera. The cartoon on the left shows it, the magma erupting out, and then the magma chamber comes empty, and the whole central part collapses, and it filled in with water. Crater Lake, the top, 10, 12,000 feet kind of disappeared. Most of it blew away. The rest caved inward. It collapsed on itself. The Long Valley and the others are huge types of calderas. Here's Crater Lake on the top, but I thought I'd throw another oddball one at you. Over here in the Mediterranean, in the Aegean Sea, there's a circular little sequence of islands, one called Thera. One called Thera. And if you study your archaeology, you might want to look up, or if you like archaeology, try to look up maybe some of the stories of the history of Atlantis, the lost realm of Atlantis. Many scientists and archaeologists are thinking that maybe Thera, a collapsed caldera, is actually the site of what might have been described as Atlantis at one time. In the Southwest Pacific, Krakatoa blew its stack. There's another one out there, Tambora, that blew. So there's lots of these great big huge supervolcanoes around. Here's Long Valley Caldera. See where this arrow's pointing? Right there? What's there geographically? Some kind of feature if you've traveled in northwestern Wyoming. Yellowstone National Park is a supervolcano. And we're really, really monitoring and watching it. There's all kinds of studies going on to see what's going on with the gases that are being vented from the mud pots, to what kind of chemistry changes are occurring in the springs and in the geysers that are on here, to see what changes are going on. That's just some of the mild surface changes we're looking at. We're also looking at kind of the seismic stuff. Okay? In fact, in one part, let me go way back to this one shot real quick. This is kind of the central downdropped area of Yellowstone, the top part of this map. The Yellowstone Caldera, right up here in the corner. It's a little basin called the Norris Basin. They just closed it to the public because of the gases that were changing in here, that in 2003, parts of it are shut down. The gases are toxic. You breathe them, they're going to kill you. So the park rangers go with gas masks and take gas checks. Something's happening. They've been doing studies with GPS, watching the ground shift up and down, doing studies with seismic, checking out the number and sizes of the epicenter map and time, showing the changes that are going on. Something is slowly happening in Yellowstone. We're just hoping it's just kind of a little burp. But apparently there's an overdue date for an eruption. Well, if this place erupts again, Mount St. Helens will look like a pimple, pardon the expression. And we will be affected by fallout of ash and a lot of stuff out here. So what are some of the things that are dangerous to us? How are people really affected by these volcanoes? What's the dangerous part? Well, pyroclastic flows, obviously. If there's a shift in sea level because of the eruptions to create tsunamis, quite common. Or the mud flows. Or simply just by the destruction of crops or the loss of water and health standards, you may get famine or other things spreading through the community. There's this whole list of these things in Table 7.1 in your text, but the top 4 here are where most of the deaths occur in that. Pyroclastic flows, tsunamis, lahars, and of course the indirect thing through famine. And that depends, I guess, on the country that you're in. Another interesting thing of looking at describing volcanoes, the volcanic explosivity index, the VEI, Volcanic Explosivity Index. Well, look at the index they've given based on material they've studied and found out about Yellowstone. It's the highest one on the scale. Got a very high VEE. I think one of the questions on the on Blackboard. And of course, here's one, Lake Nyos. I want to show you a little bit about Lake Nyos here. It has a very low VEI, excuse me. There's Tambora, Krakatoa, Vesuvius, Pinatubo, St. Helens. This is, 5. That's pretty nasty, but Yellowstone's pretty big. And it's due for one. But way down at the bottom, 0 for Lake Nyos. It's not the explosive character of Nyos, it's something else. And this is here's Lake Nyos in Cameroon, Africa. This is a little water-filled caldera, and bubbling out of the bottom of the lake, coming from the magma below it, is toxic carbon monoxide gases and carbon dioxide gases, and they're denser than air, especially the carbon monoxide. They're denser, so the gas didn't just go straight up in the air. The gas pooled on the lake and eventually came over the side, right down into a village, and killed 1,724 people. They were basically suffocated. All the animals and humans just wiped out. This gas. So what they're doing now is something totally new and kind of brand new to mitigation. They're going in and they're degassing the lake. The cartoon on the top from your text shows the bubbles coming up, coming over the edge, hitting the village on the right. Now a team of researchers have gone in there and put in wells, and they're pumping and getting the gas out and remove it. All right? And in doing that, they're keeping that toxic gas from building up inside the crater so it cannot come over the edge. So some pretty interesting ways of playing with this. Here's one. We're getting near the end here, so I thought I'd point out some other oddball things with volcanoes. If you ever go to Iceland and you happen to be flying around, looking down, and you're looking at the glaciers, and all of a sudden you see something like this big brown black spot, and all of a sudden it starts to melt and melt. What's happened is a volcanic lava flow has erupted underneath a glacier. Here's the beginning of it, and it moves very quickly. They were very concerned because it melted this so fast, created quite a flood. I'll show you the picture of it, but I want you to write that word down, Jokulap. Jokulaup. A Jokulap. A Jokulap is where a lava flow erupts underneath a glacier. In this particular example in Iceland, you can see that when it really got going and melting, it wiped out this huge whole glacier front. Here's a main highway. Highway was washed away by the flooded water. You can actually see a lot of the sediment being blown out into the ocean. It's kind of a mega quick melt. Pretty dangerous. Now, you don't find these everywhere, but where they are there, in case this ever comes up as a question, a Jokulap. So, a lot of things can happen. Here's a little animal caught up in a low spot with those gases that are denser than air. A little gas pocket. You can see this kind of little mammal. There's the skull. Gas like in Lake Nyos to volcanic ashes coming out. We've tried everything to stop this stuff, from degassing the lakes to bulldozing the lava flows to... In World War II, they tried to bomb lava flows from going in Hawaii. Didn't work. Here they're dropping water on it to cool it off. Everything we can do to slow it down to, what? Protect ourselves. The main thing we can do is monitor, try to predict, and get people out. That's the best thing. As far as totally stopping it, forget it. We have not been successful in doing that. So that's it for today, and we'll see you in the next class period.
Thank you.